So this is the 6th lecture of probability. So there's a lot of different things we can do today. We've got derangements, generating functions. I'm going to hold off on Pascal's triangle for Friday's lecture. Friday's lecture is going to be an introduction to programming. I strongly urge you to watch the video on programming in Mathematica before that to try your hand at some of the problems. The goal is not to make you the most efficient, strongest programmers possible. If this happens, that's not a bad thing. The goal is to get you to the point where if I give you something like the tic-tac-toe game and say you have 2 random people or 2 drunks playing tic-tac-toe, you might be able to find some drunks maybe in a day or two, at a certain hour, and just see how well they play. What's the chance that player 1 wins? I actually once played 20 questions with a drunk Russian mathematician, which was very interesting. All right. Let's start off with bridge. And we'll do trump splits. So in bridge, you typically bid, and one suit is determined to trump. It is a special suit. It's more powerful than other suits. Or you might decide to play the hand in no trump, in which case no suit is special. If anybody is interested in learning how to play bridge, please let me know. In previous years, I have run bridge games and instructional sessions over lunch. It is the first time I ever swore at a student for misplaying. I will try to do better, but he really, really misplayed that hand. He trumped his partner's winner and caused himself to lose. It was understandable to curse at him. Okay? So let's let hearts be trump. And let's say you and your partner have 8. So the 2 opposition have 5. And everyone has 13 cards. Okay, so this is a great way to review some of the combinatorics we've been doing. It's a great way to do some counting and see some probabilities. And it's a great way to try to see how can you apply probability. So the way you play bridge is you have 4 people typically named north, east, south, and west. North and south are partners trying to defeat the evil east-west. And you want to figure out where cards are. One way is, of course, to cheat and have mirrors or people signaling what people hold in their hands. They frown on that. So instead, we try to do mathematical inference. And we try to figure out what is the probability somebody has a given card based on their bidding. Or if I don't have any information, what are the odds that the cards are split in certain ways? So there are 5 missing trump. There are 5 missing hearts. I don't want to go into the reasons why. It would be catastrophic if all of them were in one opposition, because it would take me longer to just play rounds of cards and clean out the trump. And so what's best for me is if the trump is split more evenly among opposition. So what's the most even split it could be? 3-2 or 2-3. Okay? If it's 4-1, that's bad. If it's 5-0, it's disastrous. So here's the question. What is the probability of a 5-0, a 4-1, or a 3-2 split? For now, I don't care which person in opposition has the 5. I just care, does one person in opposition have the 5? That's why I don't have to do 5-0 and 0-5, or 4-1 and 1-4. Okay? So I have 26 cards, and I have to form 2 hands of 13. How many ways can I form the 2 hands of 13? How many ways to form 2 hands of 13? What's the answer to this? Yes?
26 choose 13.
So it's 26 choose 13. There are 26 cards. I choose 13 for the first person. I don't really need to write what I'm about to, but I just bought stock in a chalk company and I need to use as much chalk as possible today. What could I write after this? Yes? 13 choose 13. I choose 13 cards for the first person out of the 26. I have 13 cards remaining, and I choose 13 for my second person. This is, of course, overkill. It's just 26 choose 13. But it's sometimes not a bad idea when you're starting to just go through the calculation in complete detail. All right? I want to calculate what's the probability of a 5-0. So how many ways are there to choose which person gets the 5? Yes? 2. I don't like the number 2, though. I want you to say 2 in a different way. 2 choose 1. So the language we're using is almost a clue as to how to do things. It's 2 choose 1. There are 2 players. I choose one of the 2 players to be the special one to get the 5 trump. Okay? How many ways are there to choose the 5 trump for this person? 5 choose 5. There are 5 hearts remaining. I have to choose all 5 of them. They need to have 13 cards. How many more cards do they need? 8. And how many cards are available to choose from? 21. So it's now 21 choose 8. I don't need to write it here, but there's now 13 cards remaining. There's one more person. They have to get all 13 remaining cards. So this is the number of ways that one person could get all 5 trump. And it could either be east or west. So if I want to find the probability of a 5-0 split, what do I need to do? Yes? Divide by the total number of hands. So I divide by 26, choose 13. And these are all going to be rational numbers. They're going to involve factorials. And you just plug and chug. No one wants to see me plug and chug live. So I have just written down from the book what it is. When you go through at the end, when all the algebra settles, you get 9 over 230. It's a terrible 2. 230, which is about 3.91%. Okay? So what this is telling you is it's about a 4% chance that one person in the opposition has all 5 missing trump. So if you're trying to decide how likely is it, it's not that likely. All right? Let's calculate the probability that somebody has 4. So probability of a 4-1 split. All right, how do I start? Okay. So I choose one person to be special. Now what comes next? 5 choose 4. Now what comes next?
22 choose 9.
Okay, why 22 choose 9?
Because you have to finish that player's hand.
Okay, and now what?
Would you do 2 choose 1 again, or 1 choose 1?
So you could do 1 choose 1. There's only one person left, and they get all the remaining cards. So there's... And then we would divide by the number of hands, 26 choose 13. Do people agree with this? No.
Shouldn't it be 21 choose 1?
So is this 22 or 21? This is the most common mistake made in these problems. So I'm glad you said this, because it allows me to talk about this. Yes?
21 because you can't choose the other trump card.
Right, so if I do 22, then that means the heart that I didn't choose here is available to be chosen, and then the person would actually have 5 hearts. So I have to do a 21 here and exclude that card from play. Okay? So now when I do the calculation, and again, you do not want to see me doing algebra in public, this gets to be 13 over 46, which is about 28.26%. And then if we do the probability of a 3-0, I'm sorry, 3-2, we would get 78 over 115, which is about 67.83%. Okay. I'm not going to do this calculation. It's in the book. It's very similar. So we've done 3 calculations. There's something we should do now. What should we do? Yes?
Check by adding low.
Yes, we should check and make sure they all add up to 1. If they all add up to 1, did we do the problem correctly? Yes.
We have, right? Because the only options, if you've got the 5-year collector, that there's a 5 zeros split, a 4 1 split, or a 3 2 split of some sort. So it's the entire sample space.
So it's the entire sample space. These are the only outcomes. But this does not mean I have not made a mistake. It means if I've made a mistake, I've balanced my mistake with another mistake. That the number of my mistakes is at least 2. Right? This is an important concept. Right? It doesn't prove that we haven't made a mistake. It just proves if we made a mistake, we made 2 of them. Now, instead of calculating this by doing it the long way, what's the fast way to calculate the probability of a 3-2 split? 1 minus, right. And then if we check to see if they add up to 1, surprise, surprise, they add up to 1. So if you're really comfortable that you've done the first 2 parts right, you can do this part faster by just doing 1 minus. If you want to try to make sure that you haven't done a mistake, do all 3 calculations and then see, does it add up to 1? When the dust settles, it will add up to 1. If it doesn't, I apologize, I wrote the wrong numbers on the board. Okay? But whenever you can check math, it's worth checking. And this is a really nice, simple way to check. So how many people find this a appealing, fun way to do the problem? How many people want to see a faster way to do the problem? All right, let's do a faster way. So I'm only going to do the probability of a 5-0. Faster way. There are 5 trump left. What's the probability, what should we name the trump? Yes?
T, 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 and T?
No. I want them to be distinct. T1 through 5, right? Ace, deuce, 3, 4, 5. It doesn't really matter. Doesn't really matter what we use, but let's just choose 5 consecutive numbers. Let's choose the first 5. What's the probability that the ace is in the first hand? One half. What's the probability the ace is in the second hand? What's the probability the 2 is in the first hand? What's the probability the 2 is in the second hand? All right, yada, yada, yada. For 5, it's 1/2, 1/2. So each trump is in each hand half the time. So the probability all in one hand is what? So if each one is, yes?
1/2 of the 5th times 2, if we consider each hand, right? So it's 1/2 of the 5th for all in player East's hand.
Mm-hmm.
It's the same for player West's hand.
Okay.
So if we say the probability of all 5 is in East or West's hand, it's 1/2.
Okay. So then so we now need to multiply by 2. 2 to the 5th is 32. So this gives us 2 over 32, or 1 over 16. And 1 over 16 is about 6.25. Sixteen times 6 is 96, so it should be a little bit more than that. Okay. Any questions or concerns? Yes? Yeah, it really should. The answer should not depend on how we calculate. So there must be a mistake on the board, possibly more, but there's at least one mistake. Okay? Which method do you think made the mistake? The first or the second? Second. What's wrong with the second? Yeah?
Well, once you, let's say the ace goes into the first hand,
Right.
then there's 9 numbers left in the second hand. The probability that, that the second person, it changes from 1/2 after.
Okay, good. So there's 13 slots in each hand. As slots fill up in the first hand, the probability that the next card goes to the first hand over the second hand is changing. Imagine we had 14 special cards. Well, after you put 13 special cards in the first hand, there's no more spaces available. You can't put in any more special cards. The probability would have to be 0, even though each card would be in at 50-50. So the problem is these are not independent events. Once you know a card is in one hand, it makes it more likely that another card is not in that hand. So one way to really see what's going on is to look at a simpler case. So whenever you're given a problem, try to look at a smaller case where things are a little bit easier. So I'm going to look at a case of just 2 trump and 4 cards to just show what's going wrong here. How many of you know the group ABBA? ABBA, yes, one of the greatest groups of all time. All right. We will meet ABBA and hear ABBA later in this semester as they illustrate a similar counting issue. Okay? And I'm open as to what language we can do. Their original, Spanish, English, so many options. All right, so let's assume 2 trump and 4 cards total. And so just so it's the same in the book, I guess here I'm doing the 1 of spades, I guess the ace of spades, and the 2 of spades, and then the 3 of hearts and the 4 of hearts. And I want to look at all the ways we can divide them. So we have person 1, person 2. Okay. And I'll just go in the same order as I have it here. So one possibility is this person gets the 1 and the 2, and then this person would get the 3 and the 4. In the next case, this person is going to get the 1 and the 3, and this person will get the 2 and the 4. In the next case, this person gets the 1 and the 4. This person gets the 2 and the 3. In the next case, this person gets the 2 and the 3. This one gets the 1 and the 4. In the next case, this is going to get the 2 and the 4. This person gets the 1 and the 3. I'm just going through all the possibilities. And this person gets the 3 and the 4. And this person gets the 1 and the 2. So why are there 6 possibilities? Yes. It's 4 choose 2. 4 choose 2, which is 4 factorial over 2 factorial, 2 factorial, is 6 possibilities. Let's look. Note that 1 is in person 1 once, twice, 3 times. 1 is in person 1 half the time. 1 is in person 2 half the time. If I look at 2, 1, 2, 3, 2 is in person 1 half the time. 2 is in person 2 half the time. As you go through this, you see each card is in each hand half the time. Now let's look at the times when we have somebody getting both trump. That's this one over here and this one over here. So in 2 out of the 6 possibilities, it happens. So 2 out of 6 equals 1/3. You have a 2-0 split. If we assumed you just multiplied by 2, by 1/2, it would be 1/2 squared times 2, which would be 1/2, which is not a third. So if we assume that each card has a 50-50 chance, and you just multiply them, you get 1/4, and then since there's 2 ways of which person gets the 2-0, you would end up with 50% versus doing the calculation by brute force, it's a third. This is a much easier calculation to do by brute force than to do it with 26 cards and 5 trump. And it really highlights the idea of what's going on and the need to be careful. It is very easy to accidentally count the wrong thing. So we saw doing 22 rather than 21. We saw assuming independence when there's non-independence. Each card is equally likely to be in each hand. But that doesn't mean the same about pairs of cards. Okay. Any other questions about this problem? Okay. All right. So the next thing is derangements, and then we'll do generating functions. So we talked a little bit about derangements last time. And so, if I have some objects, I can reorder them. And I might want to know, when I reorder them, how often does a certain behavior emerge? And so this is going to be putting some material in the bank for later in the semester when we get to advanced combinatorics. It might be chapter 6. So derangements. So reorder 1, 2, ... n. What is the probability no one returns to their start? Sometimes the fun way people discuss this problem is they talk about a school where they just randomly give people diplomas. And what's the probability that somebody ends up with their diploma on graduation day? Okay, I can't imagine that ever happening, but there are a lot of things in network theory where you want to know how often something is hit. And if you reorder it, are you going to hit it again? Are you going to align again? And maybe every time you align, that's going to cause some issues. So we want to calculate the probability that either someone returns or no one returns. So which do you think is going to be easier, calculating the probability that no one returns or that someone returns? I'm sorry? The no one. And so how would we calculate the probability that no one returns? So we want to calculate the probability no one returns. So we're going to have different events. Let AI equal the event I is returned to their position. What do you think Aij should be? So AI is I is returned to where I started. Yes?
I and J.
Okay. Return to their starts. And what do you think we're going to assume about I and J? They're not equal. Because if I equal J, then this event is really just AI. So A5 is the probability that if we rearrange, 5 returns to where 5 started. A5-7 is we rearrange and 5 returns to where 5 started, 7 returns to where 7 started, and we don't care about the rest. The idea is we want to express complicated events, complicated probabilities in terms of simpler events and simpler probabilities. As a rule of thumb, would you rather do one damn hard problem or a large number of simple problems? Usually a large number of simple problems is a much better way to go. Not always, but frequently. So the question is, are these events easy to calculate? So what is the probability of A1? So A1 is the same as the probability of A2, is the same as the probability of AN. They're all the same. It doesn't matter who we're talking about. The probability that any of them returns is the same as all the others. Okay? So what would be the probability that one returns to their position? Do we care what happens to anyone else? When I'm asking, I want the probability that person 1 returns to where they started. Do I care about anyone else? No. All I care about is person 1. So how many ways can I arrange things so that person 1 returns to where they started? Yes? N minus 1 factorial. So person 1 has to return to where they start. That's forced on me. And now I have n minus 1 people, and I reorder them however I wish. How many ways can I order n people when order matters? So how many ways can I order n people when order matters? N factorial. So if I divide this by n factorial, that will give me the probability that person 1 returns to where they started, and the other people do something. Fortunately, this has a really nice simplification. right? N minus 1 factorial divided by n factorial, this is just 1 over n. Great. Building on our success, moving forward, I now decide I care about A12. 1 returns and 2 returns. This is the same as the probability of A13 is the same as the probability of A n minus 1n. They're all the same. So how many ways are there for person 1 and person 2 to return to where they started? So person 1 comes in first. Where do I put person 1? In their spot. So how many choices do I have for where person 1 goes? 1. Person 2 comes. How many choices do I have? 1. My kids were amazed when I was telling them yesterday that in college you can sit anywhere you want, because they've still got assigned seats. Now we have n minus 2 people that we don't care about. How many ways can they file in and sit? N minus 2 factorial, and we divide by n factorial. And so we get n minus 1. I'm sorry, 1 over. All right. This is where, how many of you have heard of proofs by induction? All right. I'm not going to go into too much detail right now. The pattern, I think, is hopefully clear. If I have the probability of I1, I2, dot, 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 IK, so I want K people, this should be 1 over n minus 1, dot, 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 n minus k minus 1. So I had 2 people, I went to n minus 1. I have k people, I go to n minus k minus 1. Okay? Any questions on this? So we can calculate the probability of all these events. And the goal is, now that we know these probabilities, we want to calculate the probability we care about in terms of these simpler events. So we've already seen something like this. When we did the probability of the union was the probability of A plus the probability of B minus the probability of A intersect B. We double counted. And so we had to throw away what we double counted. So now here we have a very similar formula. It's just a little bit more involved because we have a little bit more. And this is called inclusion exclusion. So we want the probability that no one returns. Or we want the probability that at least one person returns. So the question is, which is going to be the easier one? I think right now it's going to be nice to calculate the probability of A1 union A2 union AN. So I'm deliberately not saying what that is. Is that the probability that at least one person returns, or the probability that no one returns? This is at least one returns. So A1 is the event that person 1 returns, A2 is the event person 2 returns, AN is the event that person n returns. So you look at all of your n factorial orderings, tuples, and see, does this tuple satisfy either A1 holds, either A2 holds, either AN holds. And as long as one of them is true, then someone has returned. So this is the probability that at least one person returns. If I want to know the probability that no one returns, it's just 1 minus that. So the first thing is to say, this is just the sum, I goes from 1 to n, of the probability of AI. The probability of a union is the sum of the probabilities. What must be true for that to hold? Yes. They have to be disjoint. Do we think this is disjoint? Hell no, right? 1 and 2 could possibly sit. Out of curiosity, raise your hand if you were here yesterday. By yesterday, of course, I mean Monday. Okay. So keep your hand up if you were here on Monday. How many of you are still in your same seat as you were on Monday? Good number view. Okay. You do know you can sit wherever you want. Okay. So it is quite likely that we will have multiple people returning to their seats. Okay. One possibility is I could actually give you a seat number when you come into class on Friday. We could see what happens. But we're going to a new building. We're going to Lawrence 231, so we won't do this. This is overcounting. What do I need to subtract? Yes.
Sum of probability AI inter AJ.
Okay, so I need to, the probability of Aij, 1 less than equal to I, strictly less than j, less than equal to n. This subtracts the double counting. What do I then need to add back? What do I need to add back now? Triple counting. So it'll be the sum 1 less than equal to I, less than j, less than k, less than equal to n of the probability of Aij k. Yada, yada, yada. It keeps going on and on and on like this. So this is called inclusion exclusion. Okay? What I will do is I'll quickly show why this formula is true. What I want to do is I want to show that the left-hand side and the right-hand side count things the same way. I'm going to do this by cases. Okay? So case 1. So we have an arrangement where no one returns. So I have an arrangement where no one returns. Is that counted in here? No. This is all the arrangements where at least one person returns. Is it counted on this side? No. So we get 0 equals 0. So case 2, only person 1 returns. Because if I can do it for person 1, I can do it for person 1 and person, or I can do it for just person 2 or just person 3. Let's say just person 1 returns. How many times is it counted on the left? Once. How many times is it counted on the right? Once. It's only counted in the probability of A1. It's not counting the probability of A1, A2, because person 2 doesn't return. So in this case, we get 1 equals 1. So case 3, only persons 1 and 2 return. How many times is it counted? I guess I should say top and not left. How many times is it counted in the top? Once. From this point onward, it's always 1 in the top, right? Because at least one person is returned. Now people 1 and 2 return. How often are people 1 and 2 returning counted? In this part over here, how many times are they counted? Twice, right? Counted once from A1, because 1 returned, and counted once from A2, because 2 returned. Over here, how many times are they counted? Once, only in A1, 2. So we get 2 minus 1. I'll do one last one, case 4. Only people 1, 2, and 3 return. As we said, it's only going to be counted once on the top. And now let's look on the right-hand side. How many times is it counted here? 3 times. Because 1 returned A1, 2 returned A2, 3 returned A3. Now, over here, how many times do we count it? We've got 1, 2, and 3 returning. Yes. We counted 3 times. Somebody tell me the 3 times we counted. Yes.
1, 2, or 3, and 2.
Good. A1, 2, A1, 3, A2, 3. So we counted 3 times. Now we come over here to this term. How many times do we count them? Once. So we get 3 minus 3 plus 1, it equals 1. I'm not going to go through the rest of the algebra. This is the method of inclusion exclusion. When the dust settles, you count it the same way. You count it the same number of times both ways. But the point is, you write this very complicated event in terms of sums of easier probabilities. Okay. Any questions on what we've done so far? Okay. Everybody comfortable up to here? What I'd like to do is I'd like to erase this because I really want to keep this part of the board and argue from here. Has everybody written this part down in enough detail? This is where we don't have as much board space as I wish. All right. There's a nice way to simplify this formula and get a beautiful number. Okay? How many times do we have the event AI? You know, this kind of event. How many of these are there in this sum? Yes? Well, no, I'm asking how many? How many sums do we have here? How many summons? We have n. How should I write n? Yes?
N choose 1.
I should write it as n choose 1, or I can write it as n. I'll write it as n choose 1. And now what's the probability of each one of these? We calculated that before. It's just 1 over n. The next one over here, how many terms are there aij? How many summons are there? Well, so 1 is less than or equal to I, is less than j, is less than or equal to n. How many summons are there? N choose 2. I'm choosing two numbers between 1 and n, and they're not the same. So I choose two numbers. Whichever one is smaller, I give it the name I. Whichever one is larger, I give it the name j. So I have minus n choose 2, and then it was 1 over n minus 1. How many ways are there to choose three numbers that are distinct from 1 through n? N choose 3, and it's 1 over n minus 1, n minus 2. Okay, the algebra miracle is beginning. All right? N times 1 over n is 1. The next one, this is n minus 1 over 2 factorial. Then I divide by n minus 1. I just get 1 over 2 factorial. The next one is n minus 1 n minus 2 over 3 factorial. Divided by n minus 1 n minus 2. What's the next term? So the next term is 1 over 3 factorial. What's the next term? Yes? 1 over 4 factorial, and so on. All right, now that we've seen this, how should we rewrite 1? 1 over 1 factorial. All right. It wasn't clear at first that I should write it as 1 over 1 factorial, but looking at everything else, we should write that as 1 over 1 factorial. So the answer is 1 over 1 factorial minus 1 over 2 factorial plus 1 over 3 factorial minus 1 over 4 factorial, going all the way to 1 over n factorial. All right. So this is the probability that at least one person returns. So what's the probability no one returns? So probability no return is equal to 1 minus the probability of A1 union AN. So we just subtract this from 1, right? So we get 1 minus 1 over 1 factorial plus 1 over 2 factorial minus 1 over 3 factorial plus 1 over 4 factorial minus dot, 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 dot. Anybody recognize this number? So as n goes to infinity, yes.
Exponential x.
But what value of x? It is exponential of x, but what value of x? So e to the x is 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial. So what is this looking like? Exponential negative 1. So as n goes to infinity, the answer is converging to e to the negative 1 or 1 over e. Absolutely remarkable that we have such a beautiful answer. Okay? So this is the probability of a derangement. The probability that no one returns to where they start is about 1 over e. Yes? The probability that somebody returns would be 1 minus 1 over e. The probability that no one returns is, I think, 1 over e. Right, so I get 1 minus 1 over 1 factorial plus 1 over 2 factorial minus 1 over 3 factorial. That's why I have two 1 terms. I have two 1 terms. So the probability of a derangement is 1 over e. We will see 1 over e a couple of times in the course. It's always nice when you see old friends returning and having some real applications. Okay, any questions about this? So what I want to end the day with is a little bit of talk about generating functions. This is putting some material in the bank for later in the semester. So my philosophy is to have a really hard, painful start of the semester and kind of taper off towards the end of the semester when you're being overworked from your other courses. So we move at a fast pace in the beginning, and then we slow down a little bit as the semester ends. Okay? If people want to do more problems from Chapter 3, that's fine. If there's something you'd like me to do right now, that's fine. If not, I'll talk about generating functions. So are there any problems people want to see? Okay, so what we're going to do now is we're going to put some material in the bank for later. And so this is going to be extremely useful when we prove the big result of the course, the central limit theorem. So we're going to start with the Fibonacci numbers. The Fibonacci numbers are the source of a great deal of beauty. Did I give you the problem of calculating 1 over, I think, 998,999? And you got an incredibly strange answer involving decimal expansions of the Fibonacci numbers. It's not a coincidence. There must be something going on here. All right, so here's a quick introduction to generating functions. And so just basically bank this material. So F0 is 0, F1 is 1, and then Fn plus 1 is Fn plus Fn minus 1. So this is the recurrence relation for the Fibonacci's. One of the most important sequences in mathematics. We saw some kind of connection with this in roulette. And we talked about Binet's formula. We talked about using some linear algebra to solve that. I'm going to show you another way to get Binet's formula through what's called generating functions. It looks like magic at first. I'm going to define a new function, g of x, g for generating, to be the sum, n goes from 0 to infinity, of Fn x to the n. This is local information, the Fibonacci numbers. I put them all together, and I get this global object, the generating function. The idea is to somehow deduce information about the local numbers by some global properties of this generating function. So what I want is I want a nice closed form expression for the generating function. Now, this looks like a really bad idea, because if I knew the Fibonacci numbers, why would I be piecing them together like this? I don't really know the Fibonacci numbers, but I do. As soon as I tell you the initial conditions and the recurrence relation, can we just march down the line and generate the Fibonacci's? Absolutely. We actually know everything about them. So the idea is to use this to somehow extract that information. How many of you have taken differential equations? I was going to say if I see 3 hands, I'll be happy. I have 4. I'm ecstatic. Excellent. Do you remember series expansions to find solutions? This is very similar to series expansions. What I want to do is I want to use the recurrence relation to get a closed form expression for g of x and solve. And just to make sure that the people who are in operations research are bored, I'll use the quadratic formula. All right, so let's consider the sum of Fn plus 1, Xn plus 1. And let's have n go from 0 to infinity. This is still g of x because f of 0 is just 0. I'm just playing a game by shifting my index. Since f of 0 is 0, that term doesn't matter. This starts off with f1, x1. The reason I want to write this is I know what Fn plus 1 is. This is just the sum, n goes from 0 to infinity, of Fn, x to the n, plus the sum n goes from 0 to infinity of fn minus 1 x n, xn plus 1. All right, so let me think how I want to do this. Maybe I'll start. So now if I over here now, when I take n equals 0, now I'm in a little bit of trouble. This is going to give me an index of f negative 1. So as much as I would like to do that, maybe I'll start my sum at 1. And now if I start my sum at 1, I don't have to worry about putting in a negative Fibonacci index. That means this is no longer g of x, but it's really close to g of x. What is this missing from being g of x? This is now starting off at f2x2. I'm missing f1x1. So this is just the generating function of x minus f1x1. Now over here, I have fn x to the n plus 1. If I pull out an x, I have x times the sum n goes from 1 to infinity of fn x to the n. And over here, I'll pull out a x squared, and I'll have a sum n goes from 1 to infinity of fn minus 1 xn minus 1. Well, if you look at this is f0 x0 plus f1 x1 plus f2 x2. This over here is just g of x. Over here, this is almost g of x. It starts off as f1 x1. I'm missing f0. Well, do I really care that I'm missing f0? No. So I get, if I've done everything right, I get something like g of x minus f1 x1, which is just, f1x, which is just minus x, is equal to x times g of x plus x squared g of x. Isn't this remarkable? I started off with a series expansion for g, and now I have a simple formula for g of x. I can solve this with the quadratic formula. I may have made some algebra mistakes. I don't care. Right now, I just want you to get a sense. Is it? I'm sorry. Yeah, I can just solve for g of x. And so when we do some algebra, I don't even need the quadratic formula. Sorry. It's quadratic in x, but so if I've done the algebra correctly, I should get g of x is x over 1 minus x squared. And if I bring these over, I'll get g of x minus x squared equals x over g of x. I'm sorry, equals x over here, bringing that over, yes. So I've done the algebra correctly, and I get g of x is x over 1 minus x squared. We have a closed form solution for g of x. Now, we've talked about the geometric series formula in class. So if I have 1 over 1 minus r, I can write this as 1 plus r squared. So if I try to do that here, I would want to write 1 minus x squared as 1 minus r. So I would want r to be equal to x plus x squared. The problem is if I choose this for r, these two things have different powers. And then when I start expanding, the different terms are going to have different degrees of x. And if I want to find the coefficient of x to the fourth, it's going to come from many different places. When you take Calc 2, they show you a bunch of techniques of integration. Which is the one you hate the most? I'm sorry? No, you're not allowed to hate by parts. Integrating by parts is wonderful. I'm sorry. You have to love it. Nope. It might be so bad you've blocked it from memory. Partial fractions? Exactly. There you go, right? The partial fractions. You could write 1 over 1 minus x squared as a over 1 minus alpha x plus b over 1 minus beta x. Right? And now what we can do is we can expand each one of these. And now we get, it's going to be, if I multiply by x, I just put an x in both of these. And now I would get this is equal to a1 plus alpha x plus alpha squared x squared plus b, and then there's an extra x, I guess, bx 1 plus beta x plus beta squared x squared plus dot, dot, dot. And so when the dust settles, we now get g of x is equal to the sum, and goes from 0 to infinity, of a alpha to the n, x to the n, I guess n goes from 1, plus b beta to the n, x to the n. And this is also equal to the sum, n goes from 1 to infinity, of fn x to the n. And there's your formula for the Fibonacci numbers. You recover it from this. So we will talk a lot more about generating functions. This is just putting some material so that you can see it as a first pass now, so when we get to it later, you've already seen it. We'll stare at this a lot. But it's this idea of putting information together and then extracting from it. Okay? It's using the geometric series, which we talked about, and it's finding what's the right way to do algebra. That if we split it up with partial fractions, so there was a reason your sadistic teachers taught you that.